Good morning, my YouTube viewers. It's Crystal here. I'm just here this morning because I wanted to do a code review on Aggregate TensorFlow neural networks, and I wanted to see how Aggregate neural networks perform against single neural networks. The reason why I wanted to do that is because I've been looking at this research paper calling flexible model aggregation for quantile regression. So I'm not really doing quantile regression, but I'm doing aggregation just to see how it performs against a single neural network. And I'm going to use the Boston house prices because we've used those before, and I have a Boston house prices with a single neural network. So I can compare an aggregate neural network against a single neural network. So the first thing we do is we create our program in Google Colab. And Google Colab is a great platform to use to create a Jupyter notebook, with the exception of the fact that it doesn't have a very good undo function. So you need to be very careful not to accidentally overwrite or delete valuable code, which I have done in the past. So the first thing that we're going to do for Boston house prices is we're going to get the description of the columns, so you can see the description of the columns. MEDV, median value of owner-occupied homes in 1,000, is the sale price of the house, and that's your label or your target. The next thing that we want to do is we want to import the libraries that we're going to be using. In this particular program, we're going to be using Pandas, NumPy, sklearn, TensorFlow, Matplotlib, and Seaborn. Those are the libraries that we're going to be using. So we import Pandas, NumPy, Matplotlib, and Seaborn. We will import TensorFlow later on in the program. But what I should do really in the future, I'm going to say TensorFlow and then version of TensorFlow here, and then import all of the modules of TensorFlow later on. Then what we're going to do is we're going to read the data set. So we've got this data set off of Jason Brownlee's site. And then we're going to define the columns as CRIM, zone, indus, CHAS, NOx, RM, age, disk, RAID, tax, PT ratio, B, LSTAT, and MEDV. And then so here's the data set that we're going to be using. It has 506 rows by 14 columns. And then we're going to gather the statistics of the data set by using the describe function. What's interesting is with the MEDV, which is your label or your target, your mean is 22.5, your STD is 9.19, your min is 5, your 25 percentile is 17, your 50 percentile is 21, your 75 percentile is 25, and your max is 50. Because this data was compiled in the 1980s, so houses are worth a lot more now than they were in the 1980s. So we get info that tells you what each column is, the type of each column. So you'll notice that it's all numeric columns, so we don't have anything to impute. We check for any null values. We don't have any null values. So now what we're going to do is we're going to analyze the data frame. So we're going to check for the number of unique values in each data frame. And then we're going to use Seaborn to create a histogram of the label. And you can see you've got quite a few houses that are at the top of 50,000. So we do a value count so you can see how many times each value is represented in the data frame. And so what we're going to do here is we're going to take only the rows that appear more than once. And the reason why is because if a row appears only once, then you're not going to be able to make a prediction on it. So we take out all the rows that appear only once. But you didn't necessarily have to do that. It would probably change. If we took that out, it would probably change the error. And when we finish this code review, we can try it again and see what the error is when we take that out. So we check the target again. So you can see that there are about 100 rows that have been removed. So now we're checking Chaz just to see what Chaz looks like. And you can see you had 379 zeros and 27 ones. We check LSTAT so you can see what LSTAT looks like on a scatter plot. And LSTAT means lower status. I think that means poor people. RM is number of rooms in the house, and so you can see what the number of rooms in the house, and so you can see generally the more rooms you have, the higher the value is going to be, but sometimes that's not the case. We're going to check the heat map. We're going to check to see how all of the columns correlate to each other. So you can see that you've got two columns that have a pretty high correlation. But we're not going to do anything about that. I mean, in theory, what we could do is these RAD and tags have a high correlation. So in theory, we could take out the columns that have a high correlation to each other, which I may end up doing that in the end. Not going to do that right now, because what that would do is that would sort of like add noise to the system. Now we're going to define our X and our Y values. So your Y is df_pop medv.values.reshape -1, 1, and the neural network won't work if you don't do that. And then X equals df after you've popped out the MEDV. So now we standardize X. X equals X minus X mean over np.stdx. So our X is our standardized. Now we're going to use sklearn to split the data set into training and validation sets. So you can see your XTrain has 365 by 13 and your XVal is 41 by 13. Now we're going to import TensorFlow, and you can see that we're working on version 2.12. It's important to know what version of TensorFlow that you are working on, because this is one library that goes through lots of changes, and then so you could have deprecated code in your code, and so you need to know what version you're working on to know which code is deprecated. So we're going to set seed. So what that does is that like ensures that the outcome of the or the predictions are going to turn out the same each time. And now we have a function to build a neural network. So this is your function. It's going to be called model. Now what we're going to do is we're going to train and predict on the aggregated neural network. And so you can decide how many neural networks you wanted. And in this example, we've got 5 neural networks. So input shape equals xtrain.shape1. YPred ensemble equals np.zeros xtest.shape0, 1. And then so it says for I in num networks. And it says create and train a new neural network on a bootstrap sample of the training data. Indices equals np.random choice xtrain.shape0. Size equals xtrain.shape0. Replace equals true. Xbootstrap equals xtrain.ilock. Indices. Y bootstrap equals ytrain. Indices. Then model equals build neural network input shape. Model.compile. Loss equals mean squared error. Optimizer equals Atom. I'm going to change that to RMSPROP because I think that is what was on the earlier. Yeah, so I'm going to change that. And then model.compile, we're going to compile it, and then we're going to fit it from xbootstrap, y bootstrap. Epochs equals 50. Batch size is 32. Verbose equals 0. So I'm going to change this to epochs equals, well, let's change this to epochs. Epochs equals 100. And then what we're going to do is we're going to say, we're going to set up early stopping. Okay, we'll give that a go. YPred equals model.predict xtest. So that'll work here because we say xtest. YPred n symbol equals YPred n symbol plus YPred. Average the predictions from all individual networks. YPred n symbol equals YPred n symbol divided by the number of networks, and then you return YPred n symbol. So we set up the number of networks as 5, and then we build and predict with the aggregated n symbol. Predictions equals aggregated neural network n symbol xtrain, ytrain, xval, num networks, which is 5, and then we do our predictions. And so we calculate error. In this instance, we had an error of 4.83. But we had an error in the single neural network is 4.67. We compare our predicted values against the actual values, and then we have a data frame. So now that we tried to make all the values the same as with the original neural network, I'm going to run it again. And what I could do is I could take out the, oh, so I've got a warning. Says metric on val loss is not available. So I didn't get that yesterday. Oh, because we didn't have a monitor as val loss. We didn't have early stopping. So the RMSE was 4.49 when I tried to make the circumstances or the code as close as possible to the other one with the single neural network, and so we've got 4.667. So whenever we made the code as close as possible to the early one, it was just slightly better, slightly improved. And one thing that we could do if we wanted to was we could have removed one of the columns of data, but I don't think I'm going to do that in this instance. But we could have done that. We could have said, so it gives you instructions on how to drop out highly correlated columns. So you get the code to do that. It's not very good code. It looks like they got the code from somewhere, but there's the code there if you want it. And I think on Stack Overflow, I think you might get a bit better code. This looks like they just got the code from somewhere. Remove highly correlated columns. So here's some code to remove highly correlated columns. So they give you, there's different ways that you can do it. I think the way